The concept of dimensional deconstruction represents one of the most elegant and powerful ideas in modern theoretical physics, offering a bridge between the abstract world of higher dimensional theories and the tangible reality of four-dimensional physics. At its core, dimensional deconstruction is a mathematical procedure that allows physicists to recover the physics of higher dimensional spacetimes from lower dimensional theories, effectively building up extra dimensions from discrete lattice-like structures. This approach has profound implications for our understanding of gravity, gauge theories, and the very nature of spacetime itself, providing a computational and conceptual tool that has revolutionized how we think about extra dimensions. The fundamental insight behind dimensional deconstruction is that a theory with an extra spatial dimension can be approximated by a four-dimensional theory with a large number of gauge groups arranged in a chain or mousse diagram. Instead of dealing with the continuous geometry of a five-dimensional spacetime, physicists can discretize the extra dimension, replacing it with a finite number of sites along a lattice. At each site, there is a copy of a gauge group, and the interactions between neighboring sites are mediated by link fields that transform under the gauge groups at both ends. This construction effectively mimics the physics of a higher dimensional theory, with the number of sites determining the resolution of the discretization. As the number of sites becomes large, the discrete lattice approaches a continuous extra dimension, and the four-dimensional theory recovers the full higher dimensional physics. The mathematical structure of dimensional deconstruction is remarkably elegant. The gauge sector is formulated as a product gauge group, G, N, G, N, consisting of N identical copies of a simple gauge group, G, G, such as SU2 or SU3, where each copy, G, I, is localized on a distinct site of a discrete one-dimensional lattice that approximates an extra spatial dimension. The full symmetry, G, N, emerges naturally from gauging the local symmetries at each site, preserving four-dimensional Lorentz invariance while encoding the physics of the extra dimension through inter-site interactions. Interactions between adjacent sites are mediated by bifundamental link fields, U, I, which transform under the combined action of G, I times G, I plus 1, G, I times G, I plus 1. These link fields are parameterized as nonlinear sigma model fields, with the link field's vacuum expectation value breaking the product gauge group down to a diagonal subgroup, analogous to the zero-mode gauge boson in the higher dimensional parent theory. In the continuum limit as n infinity, the deconstructed theory recovers a five-dimensional Yang-Mills action, where the product group G, N, unifies into the continuous five-dimensional gauge symmetry, and the link fields approximate the fifth component gauge field. The compactification radius, R of the extra dimension satisfies 1 slash R tilde operator, G, F slash N, 1 slash R tilde operator GF slash N, yielding a Kaluza-Klein tower of massive modes with masses scaling as M, N, tilde operator, N, slash R, M, N, tilde operator N slash R, which matches the spectrum of the discrete model for finite N. This limit demonstrates how the four-dimensional construction faithfully approximates five-dimensional physics, including radiative corrections that remain UV finite for N greater than 2, without introducing anomalies or violating four-dimensional Lorentz invariance. This remarkable correspondence makes dimensional deconstruction a powerful tool for studying higher dimensional theories using only four-dimensional techniques. One of the most significant applications of dimensional deconstruction has been in the study of gravity and massive gravity theories. It has long been understood that certain theories of ghost-free massive gravity and their multi-graviton extensions can be thought of as arising from a higher dimensional theory of gravity upon discretizing the extra dimension. In this framework, the Kaluza-Klein modes of a five-dimensional graviton become a tower of massive gravitons in four dimensions, with the massless graviton corresponding to the zero mode. The ghost-free form of massive gravity, known as the DRGT theory, can be derived from the consistency of higher-dimensional general relativity, with the specific interactions inherited from the Lovelock terms of the higher-dimensional theory. However, the application of dimensional deconstruction to gravity has proven to be more subtle than for gauge theories. The correspondence between standard multigravity and extra-dimensional gravity holds only when one discretizes the extra dimension after gauge fixing the lapse function associated with the various lower-dimensional hypersurfaces. The lapse provides crucial structure to the extra-dimensional theory. In pure general relativity, it ensures full diffeomorphism invariance of the theory and enforces its Hamiltonian constraint. Thus, upon deconstruction, important information related to the extra dimension is missing in the resulting multigravity theory. As a result, one could never hope to recover higher-dimensional general relativity in its entirety upon taking the appropriate continuum limit. This is a significant limitation that has motivated the development of improved deconstruction procedures. The ghosts appearing in the naive discretization procedure are nothing more than a manifestation of the familiar Boulware-Deser ghost, which has plagued theories of massive gravity for decades. The recent developments in the successful formulation of ghost-free massive theories of gravity and extensions to multigravitons have transformed the situation, allowing for a reconsideration of previous arguments. By maintaining the free lapse in the deconstruction procedure, researchers have developed an improved procedure that results in multigravity equipped with additional dynamical scalar fields, whose field equations encode the Hamiltonian constraint in the extra-dimensional theory. This new theory, dubbed scalar tensor multigravity, can recover all of the equations and constraints of five-dimensional brane cosmology upon taking the continuum limit. The new scalar equations change the structure of some simple solutions that were previously allowed in standard multigravity, in a manner that exactly mirrors what one expects from higher-dimensional general relativity. The connection between dimensional deconstruction and massive gravity has been further explored through the study of cycles of interactions in multigravity theories. It has been conjectured that in multimetric theories, cycles lead to the introduction of a ghost-like instability, which, however, is absent in the multi-Vielbein version of such theories. This has been demonstrated by explicitly showing the presence of the ghost in multimetric theories in the form of dangerous higher derivative terms in the decoupling limit Lagrangian, while the Vielbein version of these theories avoids the ghost. These findings have important ramifications for the dimensional deconstruction paradigm, as the impediment to taking the continuum limit due to a low strong coupling scale is exacerbated by the presence of the ghost when these theories are constructed using metrics. Despite these challenges, dimensional deconstruction has proven to be a remarkably fertile framework for exploring the connections between higher-dimensional and lower-dimensional physics. One of the most striking examples is the exact deconstruction of the six-dimensional 2-0 theory, a highly symmetric conformal field theory that has no known Lagrangian description. The dimensional deconstruction prescription provides a mechanism for recovering the A-type 2-0 theories on T2, starting from a four-dimensional n equals 2 circular quiver theory. This conjecture has been put to the test using two exact counting arguments, comparing the Higgs branch-Hilbert series of the 4D quiver to the half BPS limit of the 2-0 superconformal index, and comparing the full partition function for the 4D quiver on S4 to the 2-0 partition function on S4 times T2 S4 times T2. In both cases, exact agreement was found, setting up a dictionary between exact results in 4 and 6 dimensions. This is a remarkable achievement, demonstrating that dimensional deconstruction can provide a rigorous path to understanding theories that are otherwise inaccessible. The concept of spherical deconstruction offers another fascinating variation on this theme. In this approach, a four-dimensional n equals 1 asterisk operator, n equals 1 asterisk operator, Suzy Yang-Mills theory with gauge group UN in its Higgs vacuum can be interpreted as a deconstruction of a six-dimensional gauge theory compactified on a two-sphere. The theory's Higgs vacuum corresponds to the fuzzy two-sphere, a discrete, non-commutative version of the usual two-sphere. In the limit n infinity, in infinity, the classical theory recovers a commutative continuum theory on R 3 1 times S 2 R 3 1 times S 2. The appearance of a six-dimensional theory can also be understood via the string theory realization of the n equals 1 asterisk operator, n equals 1 asterisk operator theory, where the D3 branes polarize into a spherically wrapped D5 brane, whose world volume theory reduces to a six-dimensional U1 gauge theory at low energies. This provides a beautiful geometric interpretation of the deconstruction procedure. The connection between dimensional deconstruction and spectral graph theory adds yet another layer of depth to the framework. In general, the Moose diagram does not necessarily have a continuum limit, and the diagram is susceptible of a complicated connection, which is a graph. Therefore, dimensional deconstruction can be generalized to field theory on a graph. This generalization allows for the construction of models of one-loop finite induced gravity using various graphs, where the UV divergent terms concern the graph Laplacian. This approach has been used to study self-consistent cosmological solutions for an Einstein universe in a graph-based induced gravity model, demonstrating specific results for cycle graphs. The graph-theoretic perspective opens up new possibilities for exploring the connections between geometry, topology, and quantum field theory. The implications of dimensional deconstruction extend to cosmology and the study of dark energy. The possibility of flat metric solutions in the presence of arbitrary Planck mass-sized cosmological constants has been investigated within multigravity theory. It has been found that for any finite n, no matter how large, no flat solutions exist without fine-tuning parameters in the potential. For an infinite number of fields, however, flat solutions exist within an infinite dimensional parameter space, viewed as a collective state that cannot be approximated by any finite n. This suggests that dimensional deconstruction may provide a new perspective on the cosmological constant problem, one of the most pressing mysteries in modern physics. The continuum limit of multigravity theories has been clarified through the lens of dimensional deconstruction. The generic continuum limit is a scalar tensor brane world, with the Randall-Sundrum model serving as a special case. This demonstrates how the discrete clockwork cosmological results map to the continuum results in the appropriate limit. The strong coupling scale in multigravity theories has been shown to depend upon the presence and structure of interactions between the different fields, elegantly rephrased in terms of the size and structure of the theory graph, which depicts the interactions in a given theory. The question of the strong coupling scale can be answered in terms of the properties of various graph-theoretical matrices, affording an efficient way to estimate and place bounds on the strong coupling scale of a given theory. This is crucial for understanding the viability of these theories as effective field theories. The uniqueness of the Einstein-Hilbert term as the kinetic term for a massive graviton has been demonstrated through a general perturbative analysis in 4 dimensions. Using dimensional deconstruction as a way to motivate a nonlinear ansatz for potential new ghost-free kinetic interactions, researchers have shown that any new interactions inevitably lead to more than 5 propagating degrees of freedom, reintroducing the Boulware-Deser ghost. The only term with 2 derivatives that does not introduce a ghost is the Einstein-Hilbert term, a result that extends to all orders and perturbations. This establishes the unique role of general relativity as the kinetic theory of gravity in 4 dimensions. The study of induced gravity in deconstructed space at finite temperature has revealed self-consistent cosmological solutions for an Einstein universe in a graph-based induced gravity model. The idea of induced gravity, where gravity emerges from the quantum effect of matter fields, is naturally realized in the deconstruction framework. The one-loop effective action can be expressed in terms of the graph Laplacian, providing a direct link between the discrete structure of the deconstructed space and the emergent gravitational dynamics. This suggests that dimensional deconstruction may offer a path to understanding the origin of gravity itself. Despite the remarkable progress that has been made, significant challenges remain. The low strong coupling scale in multigravity theories, which is associated with the mass of the lowest Kaluza-Klein mode, controls the onset of the Weinstein mechanism and is crucial to the theoretical and observational viability of the truncated theory. The inability to recover higher-dimensional general relativity in its entirety from a lower-dimensional multi-graviton theory in the limit of a continuous extra dimension remains a significant limitation. However, the improved deconstruction procedure that maintains the free lapse offers a promising path forward, potentially allowing for the recovery of the full higher-dimensional theory. Dimensional deconstruction represents a paradigm shift in how we think about extra dimensions and their relationship to lower-dimensional physics. By discretizing extra dimensions and formulating higher-dimensional theories as four-dimensional gauge theories with product gauge groups, dimensional deconstruction provides a powerful and computationally tractable framework for exploring the physics of extra dimensions. Its applications range from gauge theories to gravity to cosmology, and its connections to graph theory and induced gravity suggest that it may have even deeper implications for our understanding of the nature of spacetime itself. As research in this area continues to advance, we can expect dimensional deconstruction to play an increasingly important role in unraveling the deepest mysteries of the universe, from the hierarchy problem to the nature of dark energy, and to provide a bridge between the abstract world of higher-dimensional mathematics and the tangible reality of four-dimensional physics.